Welcome, everybody. This is the San Francisco Bay Area Association of Computing Machinery. So tonight we have a data science talk called The Alignment Problem. It's a book, and our speaker is the author, Brian Christian. He's a visiting scholar of UC Berkeley. So a little bit of background of the San Francisco Bay Area ACM. We were founded in 1957. We're probably one of the older meetups around. Show me an older one, and I'd like to hear about it. We're about promoting the knowledge of modern computing. We like to create community, support networking and hiring. We have only a $20 annual membership fee. We have, in general, about 2 monthly meetings every month, except for December. General computing, which is typically the third Wednesday of the month, and a data science SIG or special interest group, typically the fourth Monday of the month. We have many times we'll do networking or job announcements. We've done joint meetings with other societies such as IEEE or ValleyML.ai. We do have some other upcoming Zoom or webinar events. So we've got Saturday and Sunday, December 12th and 13th, part of our professional development seminar series, natural language processing with PyTorch. So Ravi Alongo is a senior data scientist. He's spoken at a number of our events in the past, including the data science camp. So to register, go ahead and get a screenshot of that link or go to our meetup site and there'll be details there. On Wednesday, January 20th, we'll have a Efficiently Protecting Software Innovations on a Global Scale, Stephen Bachman of Bachman Law Group. And we'll expect to have another data science talk on the fourth Monday of January. A few more details on the PyTorch class. So just be going through deep learning foundations, introduction to PyTorch, GPU and PyTorch training, to model training and deployment. So the schedule will be in the mornings of the weekend of December 12th and 13th. So that'll be a Saturday and Sunday, 10 to 1. So it'll be an online course. So it'll lay the foundations. So during this Zoom meeting, you can use the question and answer in the Zoom for questions or chat or raise hand for technical issues. We'll be monitoring those. Try and keep your questions not too long, more of a moderate length. Please speak closely to the PC when you speak so we can understand and hear it better. So for any job postings, please post it on the meetup comments and others people will be able to see it there as well. Martin, would you like to introduce the speaker tonight?
Yes. Brian, he spoke here before in person in 2016. The talk and the book, Algorithms to Live By, it changed the way I look for parking spots. He's a visiting scholar at the University of California in Berkeley, and he lives in San Francisco. He has appeared in The Daily Show, Radio Lab, he's lectured and won awards. He has written 3 well-received books. The Most Human is about AI, showing us what being human means. Algorithms to Live By tells us how to apply computer science, math, and logic to improve our daily lives. And his latest book is about what will happen when humans give their faith into the hands of those algorithms. As humans are used to treating the earth as theirs, we kill millions of animals for our needs and justify it with religious and philosophical reasons because we are equipped with superior intelligence and consciousness or something. But what if another intelligent being appeared and treated us like we treat those animals and the earth now? What about those AI systems that today can barely keep a car on the road, but follow Moore's laws and double their capabilities every 18 months? Those systems we are building today, they're meant to augment and help us. What if they tragically misunderstand their mission? Today's AI's decisions might make people stay in prison longer, or a disease may be misdiagnosed. Tomorrow, our bodies and infrastructure are controlled by AI. How do we prevent a scenario like Disney's Sorcerer's Apprentice, where he isn't able to get rid of the spirits that he caught? With that, over to Brian.
Well, thank you so much for the introduction. And it's a real pleasure and it's an honor to be back talking with the San Francisco Bay ACM. And I thought as a place to begin, I wanted to begin by kind of framing the alignment problem and just framing the moment that we find ourselves in, kind of culturally, sociologically, with a pair of graphs. So this first graph on the left is the ImageNet competition. I suspect many of us are familiar with the image classification competition that ran during the 2010s. And I have this chart in mind in particular because of the year 2012. And you can see that when you look at the year 2012, there's this one data point that is significantly lower than all the rest, and that is the famous AlexNet, which many people know as kind of really heralding the deep learning revolution for image classification, image recognition. And you can see that it, completely resets the bar in terms of accuracy for from that point forward. So there really is kind of this step change, this discontinuity or elbow in that. And so this stands in for neural networks, the deep learning revolution more broadly, and just kind of where we find ourselves at now in terms of machine learning and AI. The second graph looks at the proliferation of statistical risk assessment used in the criminal justice system in the United States. So you can see that it begins, actually, it's a really long history. It begins in the early 1930s. But it is not until really the personal computer revolution in the end of the 20th century that it really starts to take off. And of course, this chart only goes to the year 2000, but you can imagine what the last 20 years look like. And there was a moment where the Supreme Court Chief Justice John Roberts was being interviewed about whether he could foresee a day where artificial intelligence was kind of inextricably part of the criminal justice system. And he said, yeah, not only can I see that day, that day is here. This has already happened. So this graph for me kind of represents the, not as sexy or not as heralded progress of machine learning, data science, AI into the decision-making apparatus of society. So you can see it kind of percolating through in lending, in medicine, and of course in the criminal justice system. So these two graphs, I think, taken together, really paint a picture of where we are. We have these capabilities that are dramatically improving, and we also have these systems that are just seeping into the kind of decision-making infrastructure of society. And the combination of those two things has led many people to be, frankly, concerned about whether these systems are really doing what we think they're doing, and whether we can really feel good about them and trust them. So this is not a new problem by any means. In fact, this idea of what you can call the alignment problem, whether the objective that these systems have really reflects our intention. This goes back at least as far as the kind of founding cyberneticist, MIT's Norbert Wiener, who has this wonderful essay from 1960 where he writes, we all know the fable of the sorcerer's apprentice. And Martin, I think, alluded to this, right? The conjuring this force that is very, compliant, but if you don't take sufficient care in exactly what you tell it to do, then it quickly turns tragic, right? So Wiener writes, disastrous results are not to be expected merely in fairy tales, but also in the real world. And this is kind of the central quote. He says, if we use to achieve our purposes a mechanical agency with whose operation we cannot efficiently interfere once we have started it, then we had better be quite sure that the purpose put into the machine is the purpose which we really desire, and not merely a colorful imitation of it. So I really take this to be kind of the seminal formulation of what is now today known as the alignment problem. And really beginning in, I would say, 2015, 2016, you start to see not only this increasing concern, but really a mobilization. Really, I would say the birth of this field of AI ethics and long-term kind of technical AI safety. that for me, it's one of the most kind of harrowing and important things that's happening in computer science right now, but it's also one of the most kind of fascinating and encouraging. So what happened to me was like becoming kind of part of this community, and I really wanted to embark on this long-term project to figure out, the history of this movement. And so I spent 4 years going to all of the conferences, meeting as many of these people as I could. I ended up interviewing something like 100 different researchers and trying to paint a picture of where this has all come from, where it's headed, what kind of recent milestones we've achieved in this process, and also kind of what are the open problems that remain. Some of them are very technical, others are deeply interdisciplinary. So I want to give just a little bit of a flavor of some of the different things that arise in thinking about this question of the alignment problem. How do you know that the system is really doing what you intend for it to be doing? So I think a reasonable place to begin with that question is by thinking about the training data. Does the training data on which the system is trained really reflect the situation that you're going to be deploying the system into? And I think one of the places to start here in thinking about the alignment problem is the story of web developer Jackie Alcine, who was kind of an early adopter. He was really excited about, there was this new feature, Google Photos had started adopting, deep convolutional neural networks to automatically classify and categorize your photos. And this was kind of intriguing, kind of at the time, bleeding edge commercialization of deep learning. He was excited. He wanted to go check it out. And this is what he found. Google Photos had automatically curated a set of selfie pictures that he and his friend had taken and given it the caption of gorillas. So this was kind of the oh my God moment for Google Photos. It was just like the nightmare scenario, right? That something like this would happen. And very high profile failures like this have prompted this real kind of wave of both activism and also actual scientific research around this question of how can we prevent this sort of thing from happening in the future, right? And two of the people that I think of as being really at the vanguard of this area are MIT's Joy Buolamwini and Google Brain's Timnit Gebru. And they have done some really, I think, foundational work in kind of looking at face recognition, face classification systems with this intersectional lens, where they're breaking down the error rate both by skin type, in this case using the Fitzpatrick skin scale, and also along gender lines. And so this is just one sample slide, but you can see that if you break down the, then standard, I think end of 2017, commercial face recognition, face detection systems, you're seeing error rates in some cases that are like 10x on the darker end of the Fitzpatrick skin type scale. And when you do the intersectional analysis that includes gender as well, it's even worse. You're seeing error rates for dark-skinned women that are something like 50 or 30 to 50x what they are for light-skinned male. And this has in turn prompted a kind of reckoning, I would say, within the industry around training data. So what goes into the training data sets that are being used? I think that's increasingly becoming a question that can't be ignored. So I think it's very interesting if you look from a kind of culture shift perspective. There is a popular face data set on the web called Labeled Faces in the Wild. And this was put together in the late 2000s by scraping web images that had come from news articles. And so the people who appear in Labeled Faces in the Wild are the people who would appear on news articles in the late 2000s. So when the initial paper was published, there was this line in the paper that said, this data set clearly has biases. For example, there are not many images which occur under poor lighting conditions, and there are very few side views of faces or faces from above or below. However, the range and diversity of pictures present is very large. And to me, this is, I think, a very interesting historical just a piece of historical evidence that what people were thinking about when researchers used words like bias and diversity, they're thinking about lighting, they're thinking about the pose. You fast forward, and today, as of the fall of 2019, Labeled Faces in the Wild appears with this giant disclaimer that says, there are many demographic groups that are not well represented because we scraped these images off of news articles. There are very few children, there are very few babies, there are very few people of color that are represented proportional to their demographic representation. So we really are starting to see kind of a sea change. And of course, hand in hand with that, people are thinking about the question of diversity and inclusion in data science itself. And so we're seeing a lot of work.
Brief interruption.
Yeah.
Possibly a little controversy or an opposing thought. So Adam was asking, I object to the distinction between a colorful imitation and a real alignment. There's no magic to machine learning, only numbers and formula, which we should consider only the inputs, outputs, and whether the outputs are what we want. If not, we should adjust either our inputs, models, or expectations. We can never have an alignment, only in estimates of model behavior and the dynamic patches to solve the emergent issues. So any comments for Adam?
Yeah, I mean, I think philosophically, I basically agree with that, but the devil is in the details, right? I think even you can think of something as simple as, from a data science perspective, overfitting. You can think of an overfitting as an alignment problem, right? You trained a classifier or whatever it was for really good performance on a set of data points, but that set of data points stands in for some, test set, or for some, set of scenarios that it's going to encounter when it's deployed. And of course, anyone familiar with overfitting, regularization, et cetera, knows that there are things you have to do to make sure that it doesn't essentially get the wrong idea, right? Or fit those data points too prettily. So this is, I think, just a completely fundamental and unavoidable issue in data science. And when we start getting systems that are moving into parts of society that are difficult to quantify, then you really have this alignment problem, right? Where how do you even operationalize the thing that you want from the system? And so that's a question that is going to come up as we go along in the talk. So I'm happy to talk more about that as we go along. So one of the things that we do in order to make sure that a model is learning what we think it's learning and doing what we think it's doing is we use transparency methods, right? We try to actually visualize and understand what the network has learned, right? This is particularly of interest in deep learning, right? Where it's not immediately obvious what the model is actually learning. And I think there's been a lot of really encouraging work here too. So I think Google Brain and OpenAI's Chris Olah has done some really interesting work on getting classification systems to actually generate images, right? So you basically, we can get into the technical details if people want, but you generate some static, and then you start essentially fine-tuning that static to maximize the the category output for a particular category, right? And so you see these kind of surreal versions of what is like a maximal super stimulus for that particular category. And this can be really useful for detecting these issues of bias in the training data. So for example, here we see anemone fish, banana, parachute, those all look pretty reasonable. But when Chris Olah and his collaborators looked at the category dumbbell, you see, for example, that the dumbbells seem to come pre-attached with these kind of like disembodied arms, right? Almost without fail, they come with this kind of like weird arm sticking out of them. And that makes sense contextually, that of course that's what dumbbells are for. But this might lead someone to suspect that this network is not going to recognize dumbbells that appear on a rack or on the ground, for example. So visualization techniques, I think, are an important piece of the puzzle in terms of how we can anticipate systems that aren't going to generalize the way that we want. Someone else who I think has done a lot of really important work in this area is Google Brain's Bean Kim. She and her collaborators have developed a technique called testing with concept activation vectors, or TCAV. Again, I'm happy to drill into the technical dimensions with people afterwards if people are interested, but it basically shows you you can identify sort of higher level concepts and quantify the degree to which those higher level concepts appear to inform the categorization that the network is making, right? So if we were trying to look at a zebra model and it said stripes were the most important thing, then horse-like appearance, and then the presence of a savanna, sure, that seems pretty reasonable. If we're looking at a doctor model and it turns out that the third most important concept is being male, then that's maybe a sign that something is up, or this model is not going to generalize in the way that we actually want. And Bean Kim and her group has looked at the category of dumbbell in Google's Inception network and found that, in fact, the presence of an arm is the most predictive feature. So that kind of corroborates what Chris Ola's group had found as well. Some of these issues can be very subtle and very kind of culturally interesting. So, for example, Kim and her collaborators found that within Google's Inception network and GoogleNet, the concept of something being red was extremely foundational, intrinsic to the categorization of something as a fire truck. Well, this seems pretty normal in the United States. Fire trucks generally are red. In the United Kingdom, they're generally red, but in Australia, they are quite often neon yellow or white. And so again, techniques like this can give us kind of an early warning signal that a model that we develop in one context may not be safe or may not do what we want when we deploy it in another context. Now, just as important as these kind of geographical, demographic issues is also the temporal dimension, right? If we train a model at one point in time and run it at another point in time, it may or may not, the assumptions that are kind of present in that training distribution may or may not still hold. So I love this tweet from the Princeton computer scientist Arvind Narayanan, who says, contrary to the tech moves too fast for society to keep up cliche, commercial deployments of tech often move glacially, right? Think about all the COBOL that's still running, in the finance industry and banking, airline, mainframes, et cetera. ML models trained today might still be in production in 50 years, and that's terrifying. So we could see this even at smaller time scales. So one of my favorite examples of this comes from a computational linguistics group that was trying to reproduce the accuracy that they had seen in a recent paper. And they couldn't get their model to reach the accuracy that had been reported in this paper. And they first thought, well, maybe there was a bug. There wasn't a bug. They thought, well, maybe this original group had some kind of secret sauce that they didn't disclose in their paper. No, it wasn't that. It was simply the fact that the original paper was written in the original research was done in 2016. The group trying to reproduce the result was doing it in 2017. And this was with a text classifier or like an unsupervised kind of text prediction system that was trained by scraping language off the web. And it just so happened that by 2017, the things people were talking about and the turns of phrase that people were using were slightly different. And so you train that same architecture in 2018 and test it on held out set of 2016 data, and the performance just gets worse and worse and worse every single year. And I think this is a really useful cautionary tale, right? That constant vigilance basically is required. The world is always changing, and even something as simple as a system designed to do predictive text, right, is going to slowly kind of bleed out its accuracy over time. And there are some really interesting ways that this comes up, not only on the scale of years, but also on the scale of days. So another cautionary tale that comes from industry comes from a tech company, name redacted, but you will have heard of it, that was suddenly noticing that their ad metrics were tanking. And we're just trying to figure out what was going on. And basically what they were able to diagnose was that their ad system was using the version number of the mobile iOS as a feature. And when a new version of iOS would release, the model would suddenly notice that there was this thing called an early adopter, right? It would suddenly notice, oh, wow, there's a group of people that are all now running this new version of the operating system, and they have certain properties. They're very really enthusiastic about tech. Maybe they're more affluent on average, or they have certain interests that we can start marketing to. But every single day that passed, those predictions became less true, right? And the model, of course, was always retraining. But then the next day, whatever it learned was still being eroded by the fact that this signal, right, or this feature of just what version of the OS are you on, was just changing. What it meant for a user to be on that changed as a function of time, right? Literally on a day-to-day basis. So I think all of this serves to make us really think about this question of does the training data, is there an alignment problem essentially between like the training environment and the deployed environment? I think this comes up in all sorts of different ways. And this is something that people who work in the kind of longer term technical AI safety, even some of the people who are thinking about AI safety from an existential risk perspective, are thinking about as well. So one of the people who's a real leader in this space is OpenAI's Dario Amodei. And he and his collaborators have this seminal paper, Concrete Problems in AI Safety. And one of the things that they identify as just a fundamental problem with AI is what they call distributional shift. How do we make sure that if we train, let's imagine some future domestic robot, right? That's we train it in an office, but it might be dangerous if we deploy it on a factory, right? And this is particularly the case as AI capabilities expand, because the more that the system actually modifies its environment, then the more likely you are, of course, to end up shifting the distribution of the environments that you're in. And so the hope is, in addition to thinking about these issues of kind of inclusion and diversity, both in training data and in the industry itself, in addition to using transparency methods to try to identify problems before they actually happen and manifest in the real world, we might, as kind of a last line of defense, want systems that are automatically identify when they are out of the training distribution, and essentially say, I don't know what's going on anymore. This doesn't resemble anything I know what to do about. I'm going to defer to the humans, or I'm just going to take no action here. And there's a lot of really interesting work, both in sort of the classifier setting, but also in robotics and RL, on trying to quantify uncertainty and essentially know when you don't know something. Okay, so that's the training data. And I think the other obvious place to be thinking about this question of alignment is in the objective function, right? Does the objective function that you're training the system to optimize really reflect exactly what it is that you want the system to do? So one of the, I think, really kind of flagship examples of this question comes from the ProPublica reporter Julia Angwin, who ended up leading a team that studied criminal risk assessment software, and in particular, one of the most prevalently used criminal risk assessment tools in the US, which is called Compass. And basically how COMPAS works is that when you are arrested and your trial date is given, you either are detained before your trial or you're released before your trial. And so one of the things that judges, for example, have to decide or try to predict is whether you, if you're released, will you appear before the court to actually show up to your trial date? And are you likely to commit other crimes if you are released pending your trial? So you can think of this as kind of a pure prediction task. It's the kind of thing that ML, data science, should be really good at. And so it's become increasingly prevalent to use statistical risk assessment software to inform those decisions, pretrial detention decisions in particular. ProPublica did an analysis of this really widely used tool and found what appeared, at least initially, to be systemic bias against Black defendants relative to white defendants. The actual story was quite complicated, but it spurred an explosion, I would say, of interest in the theoretical computer science community around this question of how do we actually operationalize fairness? What does it mean to say that a classifier system is fair or unfair? One of the people who has been a real leader in this space is UC Berkeley's Moritz Hart. And he and his collaborators have a lot of really interesting work trying to kind of tease apart these different intuitions that we have about what makes a system fair and how you would actually operationalize that. So, for example, one thing is you might hope that, if someone is rated, let's say, an 8 out of 10 risk, then they should have the same probability of reoffending or the same probability of missing their court appointment, whether they are, in this case, Black or white. And that's what's known as calibration. And that has, in fact, been the standard metric that's been used among criminologists for the last couple decades. There are other ways, though, that we can formalize what it means for something to be fair. So he and his collaborators explore this idea of equalized odds or equalized opportunity, where you look at the people that are categorized by the model, and you say, you know, if you are misclassified, are you as likely to have your risk overestimated as underestimated relative to some other group? And here, commercial pretrial detention systems do really badly. So it turns out if you look at the people who are misclassified by COMPAS, Black defendants who are misclassified are 2 to 1 more likely to be mistakenly categorized as high risk when they're not. And white defendants, it's the other way around. They're 2 to 1 more likely to be miscategorized as low risk when they're not. And so having kind of coalesced some of our intuitions into this operational form, we can ask the question of, okay, well, can we satisfy multiple of these definitions at the same time? And there's been a lot of theoretical work in this area. Cornell's John Kleinberg, Carnegie Mellon's Alex Choldachova, Stanford's Sam Corbett Davies, their collaborators have all done a lot of work in this area. And basically the answer is no. So it turns out we have all these different moral intuitions that, when formalized, create constraints that cannot be mutually satisfied. So there's this really interesting question here that's kind of at the intersection of theoretical computer science, data science, philosophy, law, public policy around, well, okay, so taking this impossibility into account, now what? What do we do? And there's a conversation there, I think, that's beginning to happen, as I say, at the intersection of computer science and public policy. But backing up a little bit, I think we can ask what I think is an even more fundamental question about systems like COMPAS that do pretrial detention, which is, are we really measuring what we think we're measuring, and are we really predicting what we think we're predicting? So, for example, these systems are commonly spoken of as predicting reoffense, right? Recidivism. will this person commit a crime or not? But we don't observe that. What we observe is, are they rearrested and are they reconvicted? And that is an imperfect proxy, right? So if you think about if we're trying to predict their failure to appear for their court appointment, that's a perfectly observed variable. If they don't appear in court, by definition, the court knows about it, right? But if we're trying to predict like nonviolent crime, drug use or something like that, the vast majority of drug use is never known about by the state, right? So rearrest as a proxy for reoffense breaks down in that case. And it was very interesting for me when I started researching the history of risk assessment, that some of the earliest systems, for example, in the 1930s in Illinois, were being critiqued by conservatives. So here's the then Republican State Senate Minority Leader Elmer Schnackenberg in the Chicago Tribune saying, now, wait a minute, because a parolee isn't caught, he's listed as having made good, right? So just because this person isn't rearrested and reconvicted, they're being fed into the system as an example of someone who did not recidivate, right? And so the system will recommend releasing more people like that. I think this is a very interesting historical note, because in the 21st century, the vast majority of the criticism of risk assessment instruments is coming from the left, from progressives, who are framing the question in the other way and saying, well, if someone is wrongfully arrested and wrongfully convicted, they get tagged into the system as having reoffended, and the system will recommend detaining people, more people like that. And so this is really two sides of the same coin, right? There's another question with a lot of classifier systems, which is, do we actually have access to the ground truth, or do we only have access to the consensus of some group of people? So this is Tesla head of AI, Andrej Karpathy, who today, is thinking about autopilot on the highways and all that. But in his graduate student days, he was the human guinea pig for the ImageNet competition. And after painstakingly training himself, he was able to achieve 95% accuracy at the ImageNet task of classifying, is this a terrier? Is this a schnauzer? Whatever. And I think it's really interesting to think about, what does that 95% accuracy actually mean? It's not accurate with respect to the truth of whatever that picture actually is, because the data set is compiled just by asking people on Mechanical Turk. So to be 95% accurate is 95% accurate with respect to the consensus of random people on Mechanical Turk. Well, that's somewhat different than the actual truth of the matter. And this comes up in some cases dramatically, depending on what the category is. So this is Microsoft Research's Kate Crawford. She and her collaborators have found, for example, that many of the categories in the original ImageNet are totally subjective, right? So one of the categories is failure, loser, non-starter, unsuccessful person. So what does that mean? What exactly is this classifier being trained on, other than what a bunch of people's on Mechanical Turk's prejudices and stereotypes are, right? They just were shown a prompt that said, click on the picture of someone who looks like a loser, and this is what you get. But what does it even mean to have that data set, right? You don't know anything about the person. So we talked a little bit about the difference between failure to appear, which you can perfectly observe, and crime, which you can't, right? So in particular, nonviolent crime is extremely dependent on your interactions with the police. So for example, in Manhattan, white and black Manhattanites self-report marijuana use at the same rate, but black Manhattanites are 15 times more likely to be arrested for using marijuana than white Manhattanites are. So for that reason, we have this classifier that is predicting failure to appear and it's predicting crime. But we have some intuition that maybe one of those predictions is much less trustworthy than the other, right? And so we should disentangle these twin predictions that are coming out of the system, which is there's a growing movement along exactly those lines. There's also this question, even apart from everything that goes into actually training the model, making the model, what's the data, what's the objective function? There's this question of how is it actually used once the model exists? And that question is itself surprisingly fraught. So COMPAS is used explicitly for pretrial detention. I believe it says explicitly in the training materials, like this is not at all to be used for sentencing. But it is. There are jurisdictions that have cited COMPAS scores when determining people's sentence. And in one particularly memorable case in Wisconsin, the founder of COMPAS, the inventor of COMPAS, Tim Brennan, was personally called by the public defender as a witness for the defense to argue like this model has nothing to do with sentencing. Its predictions are completely intended to be used in this other area of the criminal justice system. They don't belong here. So I think it's worth, like, as data scientists, thinking about, do we need something in machine learning and data science equivalent to these kind of warning labels that you get in medicine, right? That's like, take this only as directed, right? Don't take it for anything else. Don't take it in any other way. It seems to me like we increasingly need something like that in data science and ML. Likewise, the COMPAS model makes a number of predictions. Some of them are called risks, others are called needs, and they are displayed in these red and green bars. And this is an attempt from a kind of a user interface UX perspective to distinguish between the things for which we actually want to essentially punish a person and the things for which we want to help them, right? So if someone is at risk of committing a bunch of crime, then maybe, incarceration is one way to avoid that outcome. But if someone, doesn't have a lot of close friends and family, right, that's a chronogenic need of the person, but that's not necessarily a risk. And you don't necessarily want to punish them for not having enough friends, right? And so the creators of COMPAS thought very specifically about, let's make one of these things red and the other thing green. But it's still the case that there are judges that cite the need score as a reason to detain someone pending their trial, right? So there is this gap between what the tool is designed for and how it's used. And then lastly, there's this question, I think, for any prediction system of what is the actual intervention that this prediction is meant to support. And so if you think about failure to appear, if you really want someone to appear for their court date, incarcerating them is one way to achieve that. But there are many ways to achieve that. And for example, there's a growing body of research showing that just sending the person a text message goes a long way to getting them to appear for their court. But it may be the case that the judge doesn't have the ability to provision a reminder for that person. And so they're purely deciding between locking them up and sending them home, right? So I think this is a big question for any deployed system, is you can make a prediction, but what is the action that prediction supports? Another famous example here happened with predictive policing in Chicago, where the Chicago Police Department was able to identify what they called a heat list of several hundred people who were at something like a 100x risk of homicide, of being victims of homicide. But homicide is so rare that even if you're at a 100x risk, that's still only about 7 people in 1,000 that are actually going to be victimized. And so the prediction was accurate. It was correctly identifying a group of people that were more likely to be homicide victims than the rest of the population. But they didn't know what to do. Like, what intervention do you do to 1,000 people? Do you just tell them to be careful? What do you do? And so it was ultimately very unclear what the system was designed for. So I think that's a huge question, is what, especially if you're making a prediction, where does that actually cash out in terms of an intervention in the world? So lastly, on this question of the objective function, I think to return to this example in Google Photos of the gorillas, right? It's worth unpacking a little bit the actual loss function that gets used in image
Brian?
classifiers. Yeah.
Quick comment. So Adam Finkel was asking, an algorithm has no mind of its own. It can only reflect its creators and users, to whom we should look and refer when it does evil. Accordingly, when a human training and use of machine learning must be regulated with the software considered dumb implement of our will rather than a smart actor or scapegoat. So,
yeah. I mean, I think there certainly are cases where there are bad actors, right? But I think a lot of these are cases where there's no conscious evil being done, right, by the actual creators. And so I think so much of what's happening in this space is how to prevent accidental harms, right, which are myriad. And yes, I mean, to some degree, you can think of the software as kind of a dumb instrument, but it's a dumb instrument that's like generalizing in ways that we don't really always understand. We don't always have visibility into. And so, yeah, I mean, I basically agree with the sentiment, but I think both as the capability in machine learning increases, and we'll talk a little bit about reinforcement learning at the end, and also as it moves throughout society, right? Just the level of vigilance required goes up, right? Whether you want to view it as dumb or not, the level of complexity, the level of sophistication goes up, right? And so we need to be thinking about these questions. In the case of something like the person who is misclassified as a gorilla, I think it's an interesting opportunity to think about the objective function of image classification systems. So most image classification systems use this thing called a cross entropy loss, which is basically like if you miscategorize any X as any not X, then you incur some constant penalty. So you can think about this as a kind of loss matrix in which everything except this diagonal is just a 1. But that doesn't really reflect the loss matrix that we have in our heads, right? So in this particular case, I mean, it was in fact already true that Google Photos had previously been documented as mistaking a white baby as a seal, for example. But that didn't generate the level of harm, the level of outrage, et cetera. Even if you're just purely thinking about it from a monetary perspective, the damage to Google of this particular misclassification was, a millionfold or more, right, of other types of misclassification. So there is a growing body of researchers. I'm thinking of Stuart Russell, for example, at UC Berkeley, but others as well, thinking about this as a machine learning problem unto itself. Can we learn the loss matrix by thinking about which sorts of classifications and misclassifications are most important to people, right? So to actually turn this into a kind of inverse reinforcement learning problem itself. Okay, so we've talked almost exclusively up till now about supervised learning. So I want to, in kind of the last portion here, change the focus to reinforcement learning a little bit. So as I think many people are going to be familiar, but reinforcement learning systems, as opposed to a classifier, reinforcement learning systems are designed to take sequences of actions within an environment that result in some kind of reward. So you can think, I mean, the canonical example is the DeepMind Atari paper, where they train with something called a deep Q network to play dozens of Atari games at superhuman skill. You've also got the success of AlphaGo and AlphaZero, which was a reinforcement learning system. And reinforcement learning is also behind some of the big breakthroughs that we're seeing, both in robotics, kind of dexterity in robotics and motion, as well as self-driving cars. So the way that a reinforcement learning system works is by maximizing some score known as the reward function. And so the alignment problem here takes this very concrete form of, does the reward function that you supply to the system incentivize the behavior that you want to see? And this turns out to be an extremely complicated problem. And we're seeing reinforcement learning, as I say, in these kind of theoretical game playing scenarios with robotics and so forth, but it's also, I think, in an underappreciated way, coming into consumer tech as well. So Facebook, for example, has talked about switching over some of their notification systems and their newsfeed and from a supervised learning model to a reinforcement learning model. So rather than simply trying to maximize the probability that you'll interact with a particular element in kind of a greedy, myopic way, it thinks about it as kind of playing this game where it can take sequences of actions. And maybe it shows you a notification that you engage with, but if it shows you too many of them, you might burn out and turn notifications off, or you might uninstall the app. And so I think it's fascinating that they are using literally DQN. The DQ network's the exact same system that DeepMind used to play those Atari games to manage something like Facebook notifications. So to me, I mean, I think we have these slogans, right, that are in the culture related to social media that say stuff like, if you're not the customer, you're the product. In this case, we might imagine something like, if you're not the game player, you're actually the Atari game, right? So Facebook is, you are an MDP, you are an Atari game that Facebook is playing. So yeah, Greg.
Question from Jeff Braswell. So, quote, no evil intentions, ... quote. But what about the case of PRC, where the objective of AI is to control individuals by reinforcing and enforcing societal conformance, jaywalking, social credit score, demerits, and et cetera? So.
Yeah, that's a good question. So the alignment problem is really about, does the system do what the creator of the system wants? And I thought a lot about things like autonomous weapons, things like the social credit score. And I actually decided not to talk about them because in some ways they're not an alignment problem in the technical sense, right? An autonomous weapon that kills someone because you want to kill that person, there's no alignment problem. I mean, there's some problem, but it's not an alignment problem in terms of the system is like manifesting the will and the intent of the creator of the system. I do think there's an important point here, however, on governance issues, right? Who is the person or people who gets to determine what the purpose put into that machine is, right? So it certainly enables governments to have a kind of force multiplier in the way that they control their society, right? It has military implications, obviously. And so I think there's also, in consumer tech, there's an incentive compatibility issue where, the tech companies that design systems have commercial interests that may or may not align, and partially but not totally align with the interests of the actual customers. So I think that is very much an alignment problem, although it's not an alignment problem in which the machine learning is the step that's going wrong, right? There's a misalignment between the person designing the system and the person affected by the system, and that's very real. And so in some ways, this is like I don't know if this is the optimistic or pessimistic version of the story, but what awaits us if and when we solve the alignment problem, within machine learning from a technical perspective, what awaits us at the end of that is that we're stuck with, needing to mitigate between the creator of the system and the person impacted by the system. So all that this technical work can do is kind of fix that middle link, right? So nothing's going horribly wrong in the middle of that chain, but you're stuck with this alignment problem. I think it's fair to call it that between people. So yeah, that is a fundamental issue. And that is why I think technical AI safety research goes hand in hand with questions of governance. Absolutely. So thinking about the technical part of reinforcement learning, how to actually design a reward function that evinces the behavior that you want to see, is an extremely complicated and fraught process. So this is a famous example from an OpenAI system that they developed to play Flash games. And in almost every game, maximizing the score is a really good proxy for winning the game. In this particular game, it's not. So this is a racing game, and their DQN or their RL system has learned to simply do donuts in this little harbor and collect an infinite amount of this self-replenishing power-up instead of actually completing the race. And so you can see all the other boats are just passing it by. And there are many cases where it's really difficult to define a reward function because the environment is so sparse. So if the things that are rewarding are very, very unlikely and very difficult, then it's going to be incredibly challenging to teach the agent how to do those things in the first place. So in the interest of time, I won't go too deeply into this, although that's a really deep question on its own. Usually what you would do to incentivize a system to achieve some really difficult objective is you give what are called shaping rewards. You can think of them as incentives. So there are several really great examples here. So there was a group of Danish researchers in the late 90s that were developing a system to navigate a virtual bicycle to a destination. So stay upright on the bicycle and reach a destination. Now, if you think about this in the kind of traditional way of like rewarding the agent when it arrives at the destination, you're going to have to wait like an unbelievably long time because the agent initially has no idea what to do. It's just going to be taking actions randomly. So what they decided to do was incentivize the agent by adding this reward shaping that was going to give it some partial credit anytime it was making progress toward the goal. So it sounds pretty reasonable. You want your bicycle robot to reach the destination, so you give it a little bit of points anytime it makes progress towards the destination. Sounds pretty good. What could go wrong? Well, I encourage you to think for a second about what might go wrong with that formulation. So it turns out that the system optimized itself to ride the bike in circles as quickly as it possibly could, because the 50% of the time that it was going towards the destination, it was getting rewarded. And the designers forgot to penalize it from going away from the destination. A similar thing happened to David Andre and Astro Teller when they were graduate students. They were working on a virtual soccer robot. And again, if your reward function is you get a point every time you score a goal, then it's going to be like impossible for your system to actually learn how to put together the extraordinarily long, improbable sequences of actions that are going to actually lead to that. So they decided to add a shaping reward. They decided to give the program partial credit for taking possession of the ball, right? Which is a normal precursor to scoring, right? That makes sense. So what went wrong here? Well, their robot ended up approaching the ball and then vibrating its paddle next to the ball, repeatedly racking up an infinite amount of possessions of the soccer ball. So there are many, many colorful stories. I loved talking to reinforcement learning researchers and hearing all of their tales of the way that their hand-engineered reward system totally blew up in their face. This is a very kind of standard part of doing RL research. So there are many ways to try to mitigate this problem. One is so-called imitation learning, also known as behavior cloning. We see this in Teslas, for example. Every Tesla has what's called shadow mode, where instead of thinking about driving as a reinforcement learning problem, they just view it as basically an imitation, a kind of a supervised learning problem, where even when your autopilot system is turned off, at least if you have the newer hardware, it is still running all the time and simply not controlling the car. But it's at each moment in time, each hundredth of a second or whatever, calculating what it would do if it were driving the car, and then comparing that to the action that you, the human driver, actually took, and uses that as an error signal. So there are many, many interesting things that can go right and wrong about imitation learning. I'll save some of that for the Q&A if you guys are interested. I want to focus just on, before I kind of wrap up here, on one area that I think is extremely interesting and promising, which is the idea of inverse reinforcement learning. So rather than forcing the human to specify a reward function that they want the system to maximize, maybe the system can infer and learn that reward function from the human themselves. So for example, this is Peter Abeel, who's at UC Berkeley, who's done a lot of really pioneering work in this area. He has done some of his early experiments were in a driving simulator. And the idea was that this inverse reinforcement learning system would observe his driving and ask itself this question of, if I assume that this person is, an optimal reinforcement learning agent, what is the score that their behavior maximizes? I'm going to assume that their behavior maximizes the score. So what's the score? And there were a lot of really promising early results where the system could learn that, in this case, Peter was trying to drive the speed limit and trying to keep to the right lane unless he was passing, and trying to avoid other cars and things like that. And this system had a very famous kind of real world success story in doing helicopter stunts, where it could watch human pilots attempt these helicopter stunts, figure out the trajectory that they were trying to fly, and then optimize that trajectory itself. So there's a lot of really encouraging work here. And there's one problem, though, in these examples, which is that it requires the human to actually provide the demonstration. So there are many things in life where what we want, we can recognize it immediately when we see it, but we can't necessarily do it. And so there's a question of, could you train systems on these objectives as well? So for me, I think one of the coolest and most encouraging studies in this area is by Paul Cristiano and his team at OpenAI, and Jan Laika and his group at DeepMind. They wanted to see if it was possible for a system to do inverse reinforcement learning using nothing but paired comparisons. So they thought of something that is really hard to actually do, but really easy to recognize. And they decided it was going to be backflips. So if you see a virtual robot in a virtual environment doing a backflip, you can immediately recognize, yes, that's a really good backflip. But if you were to actually try to control this robot with 10 degrees of freedom with a joystick or something, it's almost impossible to actually do it. It's also almost impossible to kind of manually create a reward function that rewards the torques and the angular momentum and the rotational velocity, et cetera, that constitutes a backflip. It's really, really difficult to manually do that. But you can show the user video clips and ask them, which of these looks slightly more like a backflip? So they did that. And they would be behind the scenes kind of building this reward model of, what do we think the operational definition of a backflip is, measured by torques and velocities and all that, if it would produce these paired preferences that people made. And after getting people to just choose, is the right video look more like a backflip to you, or does the left video look more like a backflip to you? Just after doing that for 1 hour, their system is now capable of doing these picture-perfect gymnastic backflips, right? It's tucking in to increase its speed. It's sticking the landing. There's even something, I would say, kind of aesthetic about it. So for me, there's something really encouraging and kind of hopeful about this, right? That we can get these systems to understand objectives that even we ourselves cannot formalize and operationalize. So I think about the instructions that they actually provided to their mechanical Turkers, and it just said, look at the clips and select the one in which better things happen. And there's something for me very beautiful about the vagueness there, right? That it suggests that, as we scale this up, we might someday hope to train systems to think about all of the things that we value, right? Fairness, transparency, et cetera, et cetera. And I'm not saying there's an easy way to extrapolate from here to there, from backflips to, these moral virtues, but it's promising, right? That I think in data science and in ML, there's kind of a tyranny of the measurable, a tyranny of the operationalizable, that you traditionally have to think about what you really want and then convert that into KPIs that you can then optimize. And then you have to make sure you're not overfitting on those KPIs and so forth. And maybe you have to find other ways to measure the bad side effects of optimizing those things and add those, right? What I find really encouraging about work like this is that it, of course, in some ways making even the reward into a black box that the system optimizes only raises the stakes. But there's something promising, right? That we're going to end this tyranny of the operationalizable and find a way to systems that can take these really kind of complicated and difficult to articulate objectives and optimize them just fine. So in conclusion, the incredible progress both in machine learning, data science, like the raw capabilities scientifically, and also their movement throughout society, right? They're seeping into the decision-making apparatus of society, has led to a huge amount of concern. But that concern has, in my view, really launched something of a movement, like an incredible, dynamic, interdisciplinary effort, across normal kind of disciplinary boundaries, that is making real progress, even in the last, 5 years, 4 or 5 years, even in the last 3 years, both in the ethical dimensions of data science, ML, and in these kind of technical safety concerns that await us further down. So whether or not you're persuaded by the long-term arguments, I think any of us in data science are facing some form of the alignment problem every day. And there's no simple prescription, as I think you can tell, but there is this growing arsenal of tools and this kind of growing frontier of scientific progress on this. And I think all sides of this community, present and long-term, ethics and safety, theory and practice, academia and industry, all sides of this, I view this as one of the grand human projects, certainly of the decade, if not the century. And I think all parts of this community have something to learn and something to teach. This problem is not going away. It's becoming more urgent. It's becoming more important. It's becoming more acute. But I think, as I say, that what we're seeing so far is incredibly dynamic and incredibly encouraging. And I would argue it has something profound as well to teach us about, not just about these scientific questions, but actually about ourselves and what it is that we value. So my mind goes back. I want to end with this line from Alan Turing. He was on BBC radio in 1952 and talking about these very, very early, obviously, experiments that he's doing in machine learning. And he says, I was repeatedly having to intervene. The system was learning too slow, or it was learning the wrong thing, or it wasn't learning what I thought it was learning, or it was learning something I didn't want it to be learning. And I was always having to kind of intervene and interrupt and correct it. And his fellow panelist interrupts him and says, okay, but who was learning, Turing? You or the machine? And Turing replies, well, I suppose we both were. So with that, I'm very happy to talk about any and all facets of this question. So thank you very much.
Thank you, everybody. One question from Jim Salzman. He said, if I could formally specify what I wanted systems to do, I would feel far more fortunate. The laws of mathematics only allow pre and post conditions. So do you have any comments you want to add to that? So
Yeah, I mean, I think it's interesting because the ability to formally specify certain things in a way only gets you so far, right? Like, so that's one of the things we're seeing in the fairness space, is that we have these like very concrete mathematical definitions of fairness, calibration, equalized odds. I mean, there was recently a lecture on like 21 distinct operational definitions of fairness. And in a way, it reminds me of that adage, a man with one watch knows what time it is. A man with two watches is never sure. And so I think certainly it is fortunate to be in a domain where you can explicitly specify, in the language of numbers, what you want. But even there, I think you have questions of generalization, overfitting, et cetera, et cetera. So I think this is a very, very deep problem.
okay, this is a question or comment from myself.
Yeah.
So I had studied for a while in cognitive and neural systems, doing simulations of the brain. And so in working on like optic simulations, it was interesting that by setting up interesting neural nets, trying to manage or mimic the optical neurons, there was emergent behavior that the neurons would get fooled by the same optical illusions that a human would. So for example, if you have a wireframe of a cube, you have a front square and a back square. So which corner is closest can switch from like the top or the bottom and oscillate back and forth. That was an emergent property. It wasn't something designed in there to do the visual simulation. It was just trying to do image recognition, but there's these emergent properties that were not designed into it by a person. So like Jim's previous comment was, he wishes he could formally specify, but not everything in these neural nets is formally specified. Like the king minus man plus woman is a queen is another emergent property. And
That's
so
right.
we don't have control of some of these things. If we don't have control, how can we try and manage them, whether it's to be in alignment with our wishes or in alignment with, say, good or bad?
Yeah, I think
Just to get your response.
that's a great point. So certainly I'm with you on emergent properties as being, one of the real sources of danger. And there is a lot of interest even in the last 12 months. So, after the book was essentially finished, before it came out, there's been a lot of interest in this question of so-called mesa optimization or inner optimizers. This idea that, in certain settings, the network may itself kind of develop an optimizer that optimizes some inner objective that's different from your objective. So particularly with huge neural networks, you get all sorts of weird problems like that. I think one of the most encouraging things in this space for me is the progress of transparency methods. So, maybe I think there's this attitude people have that, we're stuck with deep learning because it's so accurate, it's so good, and we just have to deal with this black box issue, as it comes. I think there's a lot of progress being made to break down that conventional wisdom on a lot of different fronts. So there are people, for example, Cynthia Rudin, computer scientist out of Duke, has some really interesting work on what if we took the kind of bounty that Moore's law and GPUs and all these things have given us computationally, and instead of using it to train huge models, we use it to efficiently search through the space of all possible simple models to arrive at like certifiably optimal simple models. And she's done a lot of really interesting work here in medicine and in criminal justice. And I think that's really promising. And it shows that in many cases, there really is no accuracy complexity trade-off. You can just find the optimal simple model. And there are people like, as I mentioned, Chris Olah at OpenAI. There are people at UC Berkeley working on ways to essentially regularize deep neural networks for transparency or for modularity. So if you, rather than just having a giant blob of, neural compute, if you have a modular network, then that makes it a lot easier to kind of supervise and understand the role that the different subcomponents of the network are playing. So I think there's a lot of work being done on this question of, how do we control or at least observe these emergent properties? To me, that there's a lot of really exciting work that's happening there.
Yeah, I've been following a number of papers on attention networks, where you look at what the visual network is focusing on. For an example, you train a network to be effective at learning husky versus husky versus wolf, and it seems to do very well. Then you look at the attention, and then you find out, well, where there's wolves, 90% of the time it's got snow in the background, and the model was focusing on snow, and so you didn't have enough variation in your training set. This gets back to like the distribution of the ethnic faces.
Yep.
So what you focus on is kind of relating to the distribution, but also if you find out it's focusing on the wrong things with these attention networks, then you can kind of pull away some of the emergent properties to not be so mysterious.
I totally agree. Yeah, I think saliency methods like that have a huge role to play. And again, it's one of these things where every researcher has their kind of personal stock of horror stories or sort of embarrassing moments where, that once they started to actually pop the hood and look at what the network was learning, it was not at all doing what they thought they were doing.
Right.
There was a PhD student in Oregon named Will Landecker, who was training a network to identify the presence or absence of an animal in the picture. So he had a bunch of pictures outside of animals with an animal, in it, and then others that was an empty landscape. And when it was similar to the snow example, when he actually started looking at what was activating the network, what he realized was that the network had found the pattern that if there's an animal in the foreground of the picture, the animal is in focus, and so the background is blurry. But if there's no animal in the picture, if it's just like an Ansel Adams or something like that, the background is really sharp because it's sort of an infinite focal length. And so he thought he had trained an animal detector, but he had actually trained a blur detector, right? Because it's much simpler to tell whether the background is in focus or not than it is to identify whiskers and eyeballs and all that. So this is absolutely endemic within researchers in this area. Absolutely.
Yeah. But actually, the more you know about it, the more you develop a healthy paranoia to be careful about.
Agreed. Yeah. I mean, in one part of the book, there's a discussion of image recognition in dermatology. And, there's a lot of concern among dermatologists of, okay, so I've got this iPhone app that can tell me if a skin lesion is malignant or not. But does it work under natural light? Does it work under fluorescent light? Does it work, with people with different types of skin, obviously, et cetera, et cetera. And there was a bit of a scandal where one of the systems that was looking really promising, again, they were doing this kind of saliency map analysis. And it turned out that the thing that was most predictive of a lesion being malignant was the presence of a ruler in the image, because medical textbooks, et cetera, always have like a ruler for scale. And so all the bad stuff had a ruler in it. And so it was looking for the ruler, which of course you wouldn't see in an actual patient, right? So this sort of stuff is absolutely everywhere.
Well, it tells you what to not put in your test set.
That's right.
Adam Finkel said, here, knowing when a model doesn't know would help imbue ML models to have a little bit more common sense, even if their users lack it. So having an ability to say unknown as a category might be beneficial.
Yeah, there's a lot of really, really cool work here that I can highlight. Maybe I'll stop sharing my screen just so that we can all talk more. There's a lot of really, really exciting work here. So Tom Dietrich, computer scientist in Oregon, has called this the open category problem, that implicitly when you're doing image recognition, all of the images that you're showing it are a thing. So he was doing a project for the EPA where they were identifying like bugs in a stream. and they thought, oh, this is a great use for convolutional neural networks. And they built a bug classifier that, with 90 something accuracy could tell you what type of bug, was it a gadfly, was it a mayfly, whatever it was. But when they ran it in real life, they discovered very quickly that most of the things in a stream are not bugs at all. And so your bug classifier is telling you, which bug a piece of dirt most resembles or a rock most resembles. This is, so this idea of what he calls the open category problem, and the fact that most of the things you could encounter are not in any of the categories on which you've been trained. And how do you identify that? There's another researcher named Yaron Gall at Oxford who has done some really cool work with dropout. So I don't know how familiar with certain of these deep learning techniques people are, but there's this idea called dropout, where it's sort of a form of regularization and training where you're purposefully deactivating a certain percentage of the neural network with each training example so that you encourage the network to learn kind of more robustly. It turns out that if you leave dropout on during deployment, then you get this kind of probabilistic output where you run the network a couple different times, ask it to make the same prediction with different parts of the network dropped out, and you get maybe a different answer or with different kind of confidence. And you can use this it turns out, as a really well-calibrated estimate of how certain the system is. And there are people, for example, at UC Berkeley, a PhD student named Gregory Kahn has been using this dropout model of uncertainty in robotics settings. So you have a collision predictor, and you've got a quadcopter flying around a room, or whatever it might be, and it has this model that's a collision predictor, but you're using dropout to get a measure of the uncertainty. And whenever the uncertainty gets too big, the robot just slows down. And so there's, I think, a lot of really, really interesting work there on A, how do you formalize this question of knowing when you don't know? And then B, what do you do, from a practical standpoint? What action do you take when you know that you don't know? And that might be somewhat simple with a quadcopter where you just stop or slow down, less obvious on a highway, right? So even that is a pretty interesting question.
Yeah, or a credit score.
That's right.
Martin Stein had a question. So he's currently reading or listening to Harari's Homo Deus. If you read it, how do you think your conclusions might differ from his? Or if you have read it?
I've not read it, so I would need someone to give me a summary before I could react to it.
Martin, if you want to unmute yourself, go ahead.
My question, I just thought if you had read it, it's about what humans will become in the next century, but similar kind of. I recommend reading it. It's pretty cool.
Yeah. I mean, I think if I take your question to be sort of like, what's the end game? Mm-hmm. It seems to me pretty much inevitable that something like AGI, right, artificial general intelligence, I see absolutely no fundamental reason why that won't happen. I don't think it's going to happen overnight. So people in the AI safety community are kind of divided between what you might call the hard takeoff and soft takeoff. I'm kind of a slow soft takeoff person. I think it's going to be gradual, but it also feels totally inevitable. So I think it's going to be very interesting to think about what it means to actually exist in a world where we have these systems that, for all intents and purposes, we treat as having kind of equivalent, if not greater, cognitive abilities than we do, and equally flexible. Who owns those systems? What are the incentives of those systems? How do they actually integrate into society? How do they change the way that we relate to one another? I think all of those are wide open questions, extremely interesting questions.
Mm-hmm. Thanks.
One question more, or comment more for myself to see for your comments on the whole modularity. One of the things I was thinking, I deal with a lot of Internet of Things and a lot of sensor fusion. So this machine and that machine all interacting in a plan. But thinking about neural nets as more sensors like eyes and ears, but not the brain. Have something
Yeah.
like a Bayesian network that's much more explicit to do the reasoning of the control systems,
Yep.
the closed loop PID controller. But then that would be something that could be made more explicit. After you train the Bayesian network, you could kind of see the Bayes rule between the individual network connections. And that would be easier to communicate with the clients. Because as I'm working with clients, that's always visibility and transparency is always very clear. So they may not care how you recognize if it's widget X or widget Y, but they do want to know how you're making this control decision to shut down this machine and the
Yeah.
logic behind it.
I totally agree with that. I think, I haven't seen a ton of work, at least on the kind of research side, explicitly looking at systems like this. But I think that's an incredibly good idea. And I think we're going to see more and more of that, right? Where you essentially have, you might even see it as like a local versus cloud thing, where, you've got some bipedal robot, you have to compute like the balancing and the motor skills like locally, because you don't have the latency to like phone home about like I'm about to lose my balance, right? So all of that has to be done on board. But the higher reasoning of like, you ask it, who won the 1981 World Series or something, it pings something over the web. So you might have a weird thing where essentially like the brainstem is local and the cortex is, in the cloud, right? So you can imagine things like that. And to your point though about architecture, I think that's absolutely right. So you can imagine something like, maybe at the end of the day, we're stuck with deep neural networks for the perceptual part and for the fine motor part, but we don't want to just train the system end to end. We want to have the kind of higher decision making transparent, right? And so we use something that's a little much sparser for that. There will always be arguments that people make where, inevitably the training it end to end is going to be better, but I think it's more than made up for by the transparency benefit.
I like this comment from Tom Moran. Doctors have to take periodic classes to stay licensed. Should we do that for AI systems? Particularly in your beginning comment about how long COBOL systems last or other legacy systems once they're entrenched. They tend to last a long time. And your talk about concept drift in the newspapers, I think, is very related to that.
Yeah, I mean, I think that comment also applies to people too. I mean, one of the motivations I had for writing this book is that there are many people in society who have been in their job for decades, right? If you're a lawyer, if you're a judge, if you're, an ophthalmologist, suddenly, several decades into that career, which you maybe didn't think of as a particularly technical career, suddenly, like if you're a judge, now you're being given these risk assessment scores, and you need to have some intuition about whether or not that score is reliable based on, does this person fit the distribution, or is there something weird about the data that in this person's record that makes their prediction kind of not trustworthy? So part of where I felt I could play a role as kind of as an author is to write a book that is sufficiently approachable for non-technical people, that if you're a judge, if you're whatever, a policymaker, it can be a way to develop enough of a technical intuition to know what you're doing when you interact with systems like that. But I realized that wasn't the person's point. So in terms of the actual models themselves needing to be retrained, I completely agree. And there are, to the degree that, particularly as we think about like the more ethically charged aspects of data science, to the degree that we want the world to change and become better, more just, whatever, we should expect a lot of the correlations that currently exist to break. I think more broadly, we need to sort of think about frameworks for ML that can in some way anticipate that, or can can more easily adapt to the shifts that perhaps that system itself introduces some kind of distributional shift just by existing as part of this, decision-making chain, right? It affects the data that it's going to see later.
Yeah, I mean, there was a concept of stability versus plasticity. You want to learn new things, but not forget your grandmother. You want to have drift, but you don't want the what you're retraining the model on for the convict recidivism not get drifted so much that it starts undoing the original rules it was supposed to follow in the original data set.
That's right. So yeah, this is an idea that's sometimes called catastrophic forgetting. And this is like absolutely an open problem, right? If you think about it in a reinforcement learning domain, if you're training a self-driving car, it skidded on some ice, 2,000, driving hours ago. How important is it that it prevents those weights from being updated, right? So that's an open problem.
Or should the data scientists just keep adding it? When I was doing fraud detection, I would have a 6-month data set, but I would go back a year. And for my rare fraud cases, I would reseed them in plausibly into my training data set.
That's
so
very
that
interesting.
I would retrain the fraud network because I was trying to get it to learn the subcomponents of the fraud. If you think of it as a con, they have different parts of the con. The con may get mixed together in different ways, but I want to keep different example recipes, knowing that it's going to get remixed again in the future.
That's very interesting. Yeah, so I think there's a role here for ideas to come in from cognitive science, right, and neuroscience. Like, there certain events that happen to us get forgotten, others don't. And often it's the emotional valence of that, right? That has something to do with how the hippocampus decides, like, okay, this is very salient. We're going to etch this one in. And I don't pretend to know anything about the neuroscience of that. I know a little bit about the cognitive science. So yeah, I think I would be very curious to kind of keep my eyes on that space, because I think some of these ideas of like, how do you merge a neural network with, like, long-term storage, right? Can you have neural network with like access to, non-volatile storage, right? Some kind of buffer, some kind of tape, whatever it might be. How do you decide what gets stored in that fashion? I think that's very interesting.
Offline LSTM memory states.
Yeah, exactly. Right, exactly.
Jeff Braswell was asking about any recommendations on explainable AI. And given that your talk is about the alignment problem, think about explaining how you are in alignment and how you're not in alignment. That last part was my addition, but
yeah.
Just to relate the explainable AI to your talk.
Yeah. So in terms of recommendations, in that space, I think Cynthia Rudin, Rudin at Duke, is doing some really interesting work on, as I say, certifiably optimal simple models. Someone I also think is doing really interesting work is named Rich Caruana, Caruana, at Microsoft Research up in Seattle. He's done work on what are called generalized additive models. So you can basically make a model which is a linear combination of arbitrarily complex functions of a single variable. And that means that you can visualize this model as like a series of graphs. So Caruana works in medical diagnostics. So you can see, like, this is a graph of your pneumonia risk severity as a function of age, as a function of blood pressure, as a function of, whatever. And you can visually inspect each of those component graphs as a way to kind of sanity check. So he's done some really interesting work there. And then in terms of actual explanation, like verbal explanation, I mean, there are people at Berkeley doing, like, if you strap an LSTM onto a classifier, can you get it to explain like why it classified that thing? Cynthia Rudin has herself done some work on what she calls prototype networks, where for any classification, it shows you a training data, and it says, this is the picture, what you're showing me looks like this, therefore I'm going to classify it the same way I classified that. which is often kind of the way that human minds work, right? We have these prototypical examples, and then we pattern match to that.
Legal case law.
Come again?
Like legal case law.
Legal case law is a great example. Yeah. So actually building networks that have like architectural constraints on, matching everything to a prototype is very interesting. And then lastly, in terms of like actually explaining what's going on, this is in the more theoretical side, but there's a researcher at DeepMind named Jeffrey Irving, Irving, who is very interested in the idea of debate, the idea that complicated AI systems that might be kind of beyond our ability to actually scrutinize and understand what's going on internally might be able to engage in something that looks approximately like debate. So debate is a human mechanism for accountability. It's kind of the basis of the law, et cetera. We use it in our election process, obviously, et cetera. And so there's some really interesting theoretical work on what would it actually mean for two AI systems to engage in a debate, and can you make that debate, legible to a person without requiring an overwhelming amount of that person's attention? Does the truth necessarily win, or are we just training agents to be really good, bullshit artists, right? Which is not what we want. So there's a lot of really interesting work there.
I use something like that in my fraud detection systems for financial fraud. I did not a full AI system, but the pre-processing elements going into the neural net. So I had a series of pre-processing, one I would call the prosecutor. If I interpret this, I'm going to interpret this as the worst possible case of being guilty. And then I had a defender saying, oh no, I am defending this as the most plausible interpretation that they're innocent. And then I would do a gap between the two. And then some of those types of pre-processing, think of them as various variations of Bayesian rules or multiple variable interactions on how you would interpret things that would come up with a final score that goes into algorithm X, Y, or Z, whatever you want to do prediction. So I would have these individual pre-processing types of systems. They could vary from rules to Bayesian to various other things. But they would have the pessimistic opinion and the optimistic opinion and the gap.
That's cool.
And that was the way I implemented a debate, because I found sometimes that would be helpful. As opposed to usually when you're doing fraud and you have a 1 in 10,000 or 1 in 1,000 kind of things, you're always thinking about the worst case.
Yeah.
So if you think about the gap between the worst case and the best case, that was a useful strategy.
That's very interesting. I don't know if you wrote that up at any point, but I feel like Jeffrey would be very interested in that. He's got, kind of a working demo based on image classification where, you have a judge that's seeing kind of a partially obscured MNIST digit, and so they can't see the entire thing. And then you have the truthful agent and the, deceptive agent that are trying to kind of selectively show different pixels in order to convince you to have a certain construal or another, which sounds like roughly a visual analog to kind of what you're talking about. But that's super cool. I haven't heard of like a real system using that. That's
interesting because if it was always wide, it wasn't so informative, or if it was always narrow, it wasn't so informative. But it was very interesting when they would merge together somewhat. Yeah. And that would be very strong evidence.
I think just broadly, in terms of part of what I think is really interesting about the explainability, interpretability space is that it's kind of necessarily, human, necessarily interdisciplinary. Like you actually have to think about supporting the human user. You can come up with a technical definition of transparent or explainable, but that doesn't necessarily mean it actually achieves the objective that you want. And one of my favorite examples of this, there's a study done by Jen Wortman-Vaughan at Microsoft Research and her colleagues on home value prediction. And they had a home value prediction model. And it could vary from, just a few features to a huge number of features. It could either have the coefficients of those features, the weights, like obscured or revealed. and they would show it to people under different of these conditions. And as you might expect, the people who saw it in the condition where there were few features and the weights were transparent, those people trusted the system more relative to the people who saw it with more features and obscure weights. So the people who saw it with fewer features and visible weights trusted it more, as you'd expect, but they trusted it even when it was operating way out of its training distribution and outputting total garbage. And so I think that's a really interesting kind of cautionary tale, that transparency isn't necessarily an end to itself, right? It's meant to support the actual human use case.
Well, if you can not just self-report when you don't know, but self-report when you're skating on thin ice.
Yes. Yes.
Here's an answer, but I'm not so confident about it.
Yeah.
Like if you're asking staff to give a forecast on how much time this task will take, let me know if you don't have much confidence in your task.
Yeah.
Is useful. Some
Right.
other comments, and I'll read a couple because there's a similar theme of common sense. So Bill Bruns was saying, true for some professors, but professors are human, so capable of common sense. Part of the problem is common sense is not actually something all people agree on. In other words, one person's common sense may not agree with another person's. Jeff Braswell was saying that's what decisions are in the brain, debates between networks. And then Carl was kind of continuing on in the thread, would that occur in gameplay? So, but just kind of comments on internal debate or common sense.
Right. I mean, the idea of kind of competition between internal networks is very interesting. I mean, it just makes me think of, there's a lot of work on RL systems with multiple competing objectives. Some of this goes back to like the early 90s. But how do you manage kind of multiple objectives that are jockeying for the agent's attention, and do you represent those as their own little agents essentially, or do you somehow integrate that? So there are a lot of really interesting architectural choices there in terms of thinking about the complexity of what we care about, right? We care about many different things at the same time.
Yeah. A comment from me, I've been on my data science team, we're starting to use outside data labeling vendors. And I'm not just asking for the subjects of interest to be labeled, but metadata to do residual analysis. Because sometimes in the past we would pull off the shelf models for face recognition, and I was very much aware of the past face recognition issues, but I didn't have any metadata on a per image basis. And so if I want to do error analysis by attribute A that has 5 categories, and error analysis by attribute B that has 2 categories, and attribute C. So now what I'm starting to do to avoid these biases is when I'm getting the data labeled, I'm paying extra to get metadata attributes that way we can do error analysis and see if there's errors or nooks and crannies, and then comparing this to where our future distributions are expected to be involving product management. Hey, where do you think our future customers are going to be using this product, this kind of recognition, and help them be responsible for planning what some of the future situations are going to be. So that it's not just a training set is what we happen to gather. A training set has to represent the future.
That's right.
And our error analysis. So this is part of the alignment problem, is getting the metadata to analyze it by the things, but I have to imagine and pay for all the different categories I want to analyze by.
Yeah. Well,
to try, and that's my recent efforts on alignment problem.
Yeah. I mean, it's encouraging that you're thinking about it in this way. I mean, many people who I spoke to expressed, in some cases, frustration that they can't always get that metadata. So I talked to several engineers at different tech companies, names redacted, who were saying that, they have some mandate from the executives to identify whether their product is biased in something like with respect to race or gender. But other requirements, regulatory or internal, prevent them from actually having that data. So how can they measure whether it's biased or not? So there was, yeah, I'm just, without revealing what company this was, there was a bunch of people who, yeah, had exactly this problem, and they just had to like look at pictures of people and manually say, you know, this person seems to be, you know, of this ethnic group, as far as I can sort of surmise, because they weren't actually allowed to have access to the real information. And it was a painstaking and obviously imperfect, but going through that process did reveal that the product had a bias that they wanted to fix. So it's interesting to think about. I mean, we're starting to see actually a way in which the theoretical computer science story is starting to kind of reverberate into the legal literature. So there was a University of Pennsylvania Law Review article that came out saying, in the law, traditionally, it has been the case that using a protected attribute at all is like already prima facie a presumptive legal harm. And yet the computer scientists are telling us that there are a lot of harms that can only be prevented if we have use of this attribute. So we might need to start thinking about, you know, bringing the law more in line with the computer science. I think that's really interesting.
Well, I mean, when I had some of my financial models go through legal review, like if you offer credit or reject credit, you have to go through review. And so then I would have to show my models didn't use any of those ethnicity inputs, but I would use that to do the error analysis to see if there's
Yeah.
how the error rates change by. So it wasn't used in the training of the weights, but it was used to validate there wasn't bias.
Right. So yeah, imagine trying to do that without the ground truth, and you're still expected to validate the model. It's hard, right? Yeah.
You know.
There's a really good paper. I mean, for people who are interested in this space, there's a really good paper called Fairness Through Awareness that was written by Cynthia Dwork at Harvard. That's kind of like a seminally establishes in the theoretical computer science community this idea that like it is neither necessary nor sufficient to exclude these protected attributes, that there are in fact many cases one can imagine where you need that, even in some cases in the actual training process. So that's kind of overturning this long-standing notion that I think people are coming to understand that merely because a model doesn't use a certain feature doesn't mean that it can't be, you know, sexist. Just because it doesn't know your gender doesn't by no means means that it's not sexist, right? And it may be the case that it needs to know gender in order to correct for something, right?
Or it becomes a talk show host.
Yeah.
Let's see, Jeff Braswell, are there discussions where AI algorithms or bots be given unique identifiers like decentralized IDs or verifiable credentials? When does an AI algorithm undergo changes so much that it's no longer the same identity? And as far as like tracking those. So Govind was replied and said, we do not need to track each of those algorithms, including as they get replaced or evolve. Who should be held responsible for the actions, decisions taken? If not, did we not subjugate ourselves to the AI algorithms? I don't know, any comments on the discussion?
Yeah, I mean, yeah, there's a lot. I think the question of ID, I mean, that to me is very interesting. Jack Dorsey has talked about, you know, in a sort of non-committal way, having some kind of green check mark on Twitter that says this is a person, or alternatively having something that says this is a bot account. So having some kind of identification system is not crazy. It's not totally far from what tech CEOs are already thinking about. I mean, the question, there are some like really interesting philosophical, like theory of mind sort of questions of like, you know, how much does the model change before it becomes a different thing? I think that's equally true. Like philosophers have been thinking about that in the human case for a long time. Yeah, I don't know where that goes, honestly. I mean, it's interesting for me thinking about my first book, which I wrote in 2010, which is about the Turing test, was written, I mean, it's only 10 years ago, but the state of natural language processing is like unrecognizable, right?
Oh my God, yes.
And so I really think we're very nearly, if not already, living in sort of a post-Turing test world. And so we have to think about kind of what does it mean to actually regulate speech in an environment where you can't otherwise tell the difference.
So Yash was saying, very good presentation and moderation. Thanks. Jeff Braswell was saying, interesting topic, or interesting talk, important topic, Brian. I'm amazed at your recall of so many investigators and their work. I think any other final questions, we might want to wrap up shortly. If anybody else wants to post some new questions, or if you want to repost something that I didn't ask, go ahead and add something to either the chat or the Q&A.
There's
while I'm
question.
waiting, yeah, go ahead.
Yeah, one question I'm observing in the chat, and I haven't caught everything by any means, but Adam is asking advice for someone who wants to join AI ML, like how to get started. So, I mean, I can talk a little bit about that from my point of view. I mean, AI ML is, as a whole, is, you know, enormous. But if I'm just going to sort of, for the sake of simplicity, talk about, you know, if you're interested in these kinds of alignment issues, technical AI safety, you know, data ethics, et cetera, there's an increasing ecosystem of conferences, I would say. So there's one called FACT, FACCT, Fairness, Accountability, Transparency. I believe it is actually run by the ACM, but I could be wrong about that. That has done and continues to do some very central work in this area. If you go to NeurIPS, which is just the big general ML conference, they will these days almost always have entire workshops dedicated to, you know, safety, to transparency, to ethics. A lot of the things are now, you know, entire bona fide subfields of AI. So I have a bit of a Berkeley bias just because that's my kind of home affiliation. I think there's a lot of really interesting work happening. I mean, all over the place now. I think you'd be hard pressed to find a computer science department, like if you wanted to do a PhD, that doesn't have people that are working in this area. So it has been, I think, totally transformative to watch. Even I remember talking to some researchers who went to NeurIPS in 2016 and said, "Oh, we work on safety," and were not laughed out of the room, but, you know, raised eyebrows. And then, but already by 2017, you know, the following year, there was an entire like day-long workshop on safety. There was like an entire set of meetup groups there, and so it's changing. I feel like increasingly this is just becoming part of the ML curriculum, and like it's my hope that will trickle down not only from the graduate level, but, you know, this will be part of what undergrads are thinking about, just as part of the standard CS training.
With the recent election, we might have noticed human values might differ. That split might appear in a Mechanical Turk data set. Do you have any examples of how to deal with conflicting optimizations fairly, or allowing for like a slider for that value?
Yeah, that's a really interesting question. So there's like the conclusion of the book, I list a kind of a litany of troubling assumptions that get made even in the AI safety, you know, ML ethics literature that are kind of things that might give us pause, but in a more positive frame, you know, kind of exciting avenues for research. One of them is exactly what you're describing, which is that people have different values, different beliefs, and it's implicit in, for example, in a lot of inverse reinforcement learning. You're collecting these demonstrations, or you're collecting trajectories, or you're collecting, you know, preferences, paired comparisons. It's generally assumed implicitly or explicitly by the mathematical framework that you're using, that they're all coming from the same person, or they're coming from people who basically have the same idea in their heads. It's less clear what to do when that's not true. Let's just hypothetically imagine that you're Tesla and you're collecting this imitation learning data from drivers, and you notice that 50% of people go right to avoid a median and 50% of people go left to avoid a median. Well, you obviously don't want to split the difference and smash into the median. So there's a lot of interesting work on trying to identify when you might want to have, a mixture model or something, some way to account for the fact that you're getting heterogeneous data. This is totally an open research problem. I know people, working on this for their PhDs. As far as I know, it's still pretty underexplored. And I think broadly, there's also a question of, for anyone who has seen, has children and has seen the kids like fight over Alexa, play this song. No, Alexa, play that song. There is more broadly in the kind of AI safety community, this question of how do you, serve the preferences of a heterogeneous group of people? Do you have to average them? Do you have to kind of randomly switch between them? Do you try to take actions that will be kind of Pareto improvement, but not make anyone less well off? I mean, there's a huge space for complexity at kind of dealing with that multi-user setup. So I think that's unexplored terra incognita, but as you point out, increasingly pertinent. So I think the more people who thinking about that, the better.
Well, thank you so much for your time. It's been a wonderful talk. There's been a lot of engagement, a lot of people asking questions. So a lot of good interaction here. So
yeah, it's been my pleasure. So thank you very much for having me. And
okay.
Yeah.
Well, on behalf of everybody, thank you very much.
Thanks so much. Yeah.
Okay. And then also there's on the chat channel, there's a link to get the ebook, audiobook, hard copy books. So check out the chat channel. Please help support your speaker. So, and then would it be possible to get a copy of your slides to post later on? We would, or if you want to post a link just on the meetup page for this event, there's a comment section. You can just add a link there. If that'd be fine, then people can find it as you post it.
Sounds great.
Okay. Well, thank you so much, Brian.
Absolutely. My pleasure. Thank you.
Thank you. Bye.